Hello, welcome to Calculus 1, Lesson 2A1. What is a derivative? Part 1. The burning question that we're going to start with is, how do we find the slope of a tangent line? So we're going to start with secant lines. Okay, so what's the difference? Secant line is a line that goes through 2 points that are on the curve. What we want to do is we want to take one point and slide it close to the other so that it becomes a tangent line instead. Okay? What exactly is a tangent line? That's a line that touches a curve at exactly one point. Okay, so this, if I've drawn this perfectly, this line here is only touching the curve at that singular point. Okay, so if you have some other curve, if this is the tangent line there, it doesn't touch the curve at any other spot other than that one. Okay, if you pick up a pencil and any round object like a coffee cup, you can see, if you lay the pencil alongside it, you can see that it only touches at one little spot. It comes close to touching near there, but doesn't actually touch. Okay, so rather than making you render sliding this point closer until it becomes this line, in the theater of your mind, let me show you an animation. So this is something I threw together in GeoGebra to demonstrate what's happening. H is going to be a teeny tiny difference. Okay, so H is the difference of two different x values. The point C, f of C, is a point on your graph that you're interested in finding the tangent line for. Okay? When h is a tiny difference, c plus h is going to be an x value that is close to c. Okay, so that c plus h is your second x value for your secant line. Evaluate that at f, you're going to get a y value for that second x value. Then we're going to take a limit as h goes to 0, which will slide one point on top of the other until it becomes a tangent. Now, in this little doodad here, I made it where h can't go any smaller than 0.01. So the line is not perfectly on top of that other point, but it's very, very close. Okay, so with h, that tiny distance being 0.01, this line is almost tangent at that spot. Okay, so let's put some symbols to that. Consider some x value, c. Then if we evaluate the function at c, we get a y value. So we get c, f of c is a point on the graph of f. H is a tiny distance, so c plus h is another x value. So we're going to work with two x values, c and c plus h, which gives us two y values, evaluating the function at both of those spots. Okay, so we're working with 2 points which are on the curve. We're going to draw a secant line that goes through them and take the limit as h goes to 0. And just as a quick note here, some textbooks do like to use delta x instead of h, and that's okay. So let's talk about slope a little bit. We're going to use slope of the secant line, take a limit of that, and that'll give us the slope of the tangent line. Right, so slope, we think of change in y over change in x. Change in y is the difference of your two y values. Change in x is the difference of your two x values. Okay? You can also write that in terms of evaluation at a function. So your y values are what you get when you evaluate your function at your two x values. All right? And now we're going to choose these carefully. We're going to say x1 is going to be c plus h. x2 is going to be c. Then we get our y values by evaluating. And then something nice happens in the denominator as well. x1 minus x2 is c plus h minus c. And then those c's will cancel, so that denominator is just h. All right? So we're going to take this information and plug it into the idea of slope, along with a limit that's going to let h go to 0. And here's how we get the slope of the tangent line. So assume that f is defined and continuous near C. The slope of the tangent line at C is going to be the limit as h goes to 0 of f of c plus h minus f of c over h. Okay. The quantity f of c plus h minus f of c is called the difference quotient. And you might see this defined with an x instead of a c also. Either way, you can call that difference quotient. Okay? Let's talk about how to find f of c plus h. We want to think about evaluating that function at c plus h. So for example, let's find f of c plus h if f of x is this friendly neighborhood quadratic here, and let's say c equals 3. Alright, well first of all, when you evaluate a function, a smart way to do that is to rewrite the function with all of the x's replaced with empty parentheses, like so. If you do this step first, you'll never have to worry about messing up your signs or your FOILs or your distributes or anything like that, okay? Once you have it written out this way, put in the parentheses what you want your x value to be. In this case, our c is 3, so c plus h is going to be 3 plus h. So we'll put a 3 plus h in each of those empty parentheses. Now, common pitfall here. 3 plus h squared. What is that? How do you deal with that? It is not 3 squared plus h squared. We need to FOIL that. Okay? If you FOIL, here's a shortcut for you, because I hope that if you're in Calc 1 you know how to FOIL. I don't write out the first, outer, inner, last every time I FOIL. I remember we square the first thing, we square the second thing, you put the product in the middle, but it's double because this is your outer and your inner. And then this here is going to be plus and plus. If it were a minus in between, then this middle one would turn into a minus. Okay? So it's square the first, square the second, twice the product. Okay, square the first, square the second, twice the product. Cool? Now here we're going to distribute the 2, so I'll have a 6 plus 2h and a plus 1. Okay, do I have any like terms? I have a 6h and a 2h. So, okay, I've got an h squared plus 8h plus 15, 16. So that is f of 3 plus h. Okay, so now that we know how to find f of c plus h, let's go ahead and find the slope of a tangent line given some function. Find the line that lies tangent to this linear function when c equals 2. Now, if we stop and think about this for a minute, this function is linear. It looks like this. 1, 2, 3, y-intercept of negative 3, and a slope of 2. So it's going to look like that. What does it mean to be a tangent line to a line? A line can't touch another line only in one spot unless it's intersecting. That's not a tangent. The only way to be tangent to a line is to be right on top of it. So when your x value is 2, which will be the point right about there, the tangent line is going to sit right on top of it, going through 2. Let's see if the math supports that. F of something is 2 times something minus 3. So f of 2 plus h is 2 times 2 plus h minus 3, which is 4 plus 2h minus 3, and that reduces to 2h plus 1. F of c, or f of 2, is 2 times 2 minus 3, which is 1. Now we want to take limit as h goes to 0 of f of c, yeah, I'll just put c plus h there, f of c plus h minus f of c all over h. Substituting those in, we're going to have f of c plus h, we said, is 2h plus 1, and f of c is 1. All of that is over h. Okay, what happens in our numerator? We have 2h plus 1 minus 1, which is 2h. Nice cancellation of the h's. So I have limit as h goes to 0 of 2. And the number 2 doesn't care what h is. 2 is 2 no matter what h is doing, right? No funny business with letting h be 0 here. So that just equals 2. That's the slope of the tangent line. And that is consistent with what I said before. The slope is 2. And this is linear, matches the slope of the original. Alright, so that linear example is actually kind of boring. Let's do a quadratic. We have a function x squared plus 1, and our c is going to be 1 this time. F of something is something squared plus 1. F of c plus h is going to be yellow, and it's going to be 1 plus h. Foiling this out, I'm going to have an h squared. I'm going to have twice the product of these two things, so 2 times 1 times h is 2h, and then also plus the 1 squared would be 1, and then an additional 1 makes 2. So foiling that out and combining like terms, that's what we get. F of 1 is 1 squared plus 1, which is 2. So we want to do limit as h goes to 0 of f of c plus h minus f of c all over h. Plugging some stuff in. F of c plus h is going to be h squared plus 2h plus 2. F of c is 2. all that is over h. Then what happens? Up here in the numerator, these 2's are going to go bye-bye. So then we've got an h squared plus 2h up top. And I can pull an h out of those. So I'll go ahead and show that in this step as well. h plus 2 over h. Cancel there. So we've got limit as h goes to 0 of h plus 2. Now, there's no more funny business. H is allowed to be 0 because h plus 2 doesn't have any funny business. So I'll go ahead and let h be 0. And we get 2. Notice, though, that it said find the line. So we're not done. That's the slope. We want to find the equation of the line. Find the y equals mx plus b equation of the line. So I'm going to take y equals mx plus b. Alright, my slope is going to be 2. My x value is going to come from the fact that f of 1 equals 2. That tells me that the point 1, comma 2 is on the graph. Okay, so that means my x is 1 and my y is going to be 2. And b is something we don't know yet. Okay, I call this the find b method. For finding the equation of a line. So plugging everything in, we'll have 2 equals 2 times 1 plus our unknown b. Solving that for b, we'll find that b equals 0. So our final answer is going to be y equals the m is 2 and the b is 0. Okay, so what's happening here is you're going to think back to your algebra class. We are looking for a line whose slope is 2 because that's what this limit told us, and it goes through the point 1, comma 2. Okay, let's take a look at that on a graph. Alright, so here's our function x squared plus 1. The point we're interested in has an x value of 1, so our c was 1. And then if I plot y equals 2x, that'll lie tangent to that curve right there. Okay, so the slope of this line, the 2, comes from this limit, but the point in question still needs to be on the graph of your original function, which is our parabola. Alright? Here's an interesting question. Can functions have horizontal tangent lines? Yes, they absolutely can. And we're actually going to see some interesting things that happen to functions when they have 0 for their slope of the tangent line. Let's try f of x equals x squared at c equals 0. Let's visualize it first. X squared is your regular parent function parabola. When the x value is 0, the tangent line is actually just going to be the x-axis, which is the equation y equals 0. Okay, so hopefully that's what we're going to get. Alright, let's set this up. F of 0 plus h, ooh, that is just f of h, which is h squared. F of 0 equals 0 squared, which is 0. So when we try to set up limit as h goes to 0 of f of c plus h minus f of c all over h, it looks like limit as h goes to 0 of, we've got h squared, and we've got a 0. Those two things are being subtracted, and we've got an h squared in the denominator, or regular h in the denominator. H squared minus 0 is h squared. H squared over h is just h. Limit as h goes to 0 of just plain h. Okay. Is there any funny business with h going to 0 here? No, I can go ahead and let h become 0 in this expression, and so I get a 0. That's the slope of your line. So you want a line with slope equals 0 and a point 0, 0. The only such line is y equals 0, just like we thought was going to happen. What about vertical tangent lines? Can they have vertical tangent lines? Yeah, but sometimes those limits aren't as easy to evaluate. So I'll show you a graph, but I'm going to spare you the gory details of doing that limit out for now. Okay, your cube root function, x to the 1/3, is the same as cube root. That does have a vertical tangent line right at 0. Okay, the graph looks like it wants to go vertical for a brief moment before turning the other way, in a sense. Okay, but functions don't like vertical lines, right? If you had a function like that, that's going to fail the vertical line. If you had a graph like that, that's going to fail the vertical line test. That's not a function. Okay, vertical lines that touch the function more than once. Vertical lines that touch a graph more than once show that graph is not a function. That's not what's happening here, though. This vertical line is only actually intersecting that graph at this one and only point. If you were to zoom in really, really close, you would still see a little gap in between, like that gap right there. No matter how far in, you might have to zoom in really, really close to be able to see it. But if your x is non-zero, then this line is not touching that point. Okay, so this is a truly vertical tangent line. The limit there is a little bit messy. If you wanted look like this. Actually, this one's not too terrible, but I'll leave that as an exercise to the reader. I'm sure you could do that if you tried. Next, I want to talk about what if c is arbitrary. What if I want to set it up so that I could do this for any c that I wanted? Can I create a function that will output the slope of a tangent line at any x value we want? So picture f is some function. Okay, maybe we've got some x values. We have 1, 2, 3, 4, or an arbitrary x. And we say, I want to find the slope at all of those possible x values. So the slope of the tangent line is going to be found when c equals 1, 2, 3, 4, and maybe even just an arbitrary x. If I do this, does this create a function? Does it create something that can be calculated at each x value? And would it pass the vertical line test if I did? The answer to that question is yes. And when you do that, that's called finding the derivative. So let f be a function. The derivative of f at x is the slope of the tangent line at the point x, f of x. That is a function, and it's going to be defined. We're going to use the symbol f prime of x, so it's like a little tick mark up by the f. We say that f prime. That's still going to be a limit as h goes to 0. It's going to be just like what we did before, but the c is going to be an arbitrary x now. Okay, we don't have an actual number for x. We're going to let it be an x. So let's see what that looks like. So we have f of something is something squared plus 1. Now I don't want to plug in a c plus h, I want an x plus h. Just like that. Okay, it's still tempting to distribute that squared here. This is still a FOIL. Super common pitfall there. Remember to FOIL. This is going to look like x squared plus 2hx plus h squared plus 1 after you expand that all out. Right, so we've got both x's and h's happening. We've got two different variables. This term here, it's just plain f of x. Hardly worth my time to rewrite it, huh? Now we want limit as h goes to 0 of f of x plus h minus f of x all over h. So let's substitute. F of x plus h is going to be all this nonsense, x squared plus 2hx plus h squared plus 1. Your f of x is x squared plus 1, and those things are being subtracted, and that's all over h. Now, I made a mistake here, and I made it on purpose because it's a super, super common mistake that's going to mess you up if you're not really, really careful. Pause your video real quick and see if you can figure out what is my mistake that I made here in substituting my f of x plus h and my f of x. Did you find it? This needs parentheses here. You're subtracting the entire quantity f of x. In fact, you could, if it makes you feel better, you could put parentheses around this too. These ones are not so important. Okay? But what's really important is that this negative sign, that subtraction in between the f of x plus h and the f of x, it needs to be able to talk to the entire function, f of x. Okay, and then as I go through the next couple steps, you're going to see that if we didn't have that parentheses there, that one's going to be positive when it should have been negative, and that's no bueno. So I'm going to have an x squared plus 2hx plus h squared plus 1 minus h squared minus 1 after that is distributed all over h. Cool. Let's look for any cancellations. I do have a plus x squared and a minus x squared. I do have a plus 1 and a minus 1. So I'm left with a 2hx minus h squared. From there, I can pull out an h from the top. So h times 2x plus h over h. I can cancel an h. So I've got limit as h goes to 0 of 2x plus h, and now there's no more funny business. I'm allowed to let h go ahead and be 0, and I get 2x, which is going to be my f prime. Okay, your answer is almost always going to have an x in it when you're asked for the derivative. Okay, when you're asked for the derivative, your answer has x's. There's a situation where it doesn't, but almost always it will have x's. When you're asked for when you're asked for slope of the tangent line, your answer is a number. And when you're asked for the equation of the tangent line, you're going to have some kind of y equals some number times x plus some number as your final answer. Okay, so depending on what the question's asking, if you're asked for the derivative, it's a function of x. If you're asked for the slope of the tangent line, your answer is a number. If you're asked for the equation of a tangent line, then your answer is a linear function. Right? We're starting to get a little bit about what a derivative is. Stay tuned for part 2. Keep practicing and have a wonderful day.